Hello all. In last video, we saw what is potential, what is potential difference, and what is the potential at a particular point due to a point charge. If the point charge is placed in origin, if the point charge is placed in the point where other than origin. So in this video, we will see what is the expression for potential in different charge distribution. First, we will see the what is the potential due to a line charge distribution. Consider, as shown in this figure here, consider a line charge with a charge distribution of rho L, and in that charge distribution, consider a small elemental area, elemental line, the small elemental line which is dl dash, so which is at a distance of r dash from the origin. So which is at a distance of r dash from the origin. This dl dash is consider this dl dash has a charge density of rho L of r dash. Rho L of r dash is the charge density at this elemental area. Rho L is the charge density in whole line charge, and rho L dash is rho L of r dash is the charge density at dl. And now I want to find what is the potential at point A due to this line charge, where point A is placed at a distance of r from the origin. Now, to find the distance between this point A and distance between this dl, the elemental area, what is the distance between A and dl? So I can write the magnitude of vector r minus vector r dash, which is equal to r. I am taking the capital R, which is equal to magnitude of r minus r dash, as we saw in the vectors chapter. So we can find the distance between 2 points by using the vector difference, subtracting two vectors and taking magnitude of that subtracted result. We will get the distance between 2 points. Now I want to find what is the potential at this point, and you know that I can write charge at the particular elementary area as charge density into length. The charge density into length can be, that differential length can be written as dq. So dq is rho L of r dash into dl dash. So where rho L of r dash is the charge in this small elemental area. Is the charge in this small elemental area is rho L of r dash. So dq can be written as rho L of r dash into dl dash. dl dash is the small elemental length, and dq is the charge at this particular elemental length. Now we have to find what is the potential. You know the expression for potential, that is the potential at this small area can be written as dq divided by 4 pi epsilon naught into length between, distance between point A and dl is r minus r dash. So which can be written as dq divided by 4 pi epsilon naught into r. Now substituting what is dq. So dq, you know that rho L of r dash into dl dash. Substituting that this in this equation. Now you will get, so it will be rho L r dash into dl divided by 4 pi epsilon naught. So that is the potential at that differential length. Now to find total potential due to this line charge, what we have to do? We have to take integration of dVA. So we can write VA is integration of dVA, so which is dq divided by 4 pi epsilon naught r. So if you substitute dq as this rho L of r dash into dl dash, you will get the potential at point A due to a line charge is equal to rho L of r dash divided by dl dash divided by 4 pi epsilon naught r. Now this rho L of r dash will be equal to rho L if the charge distribution in the line charge is uniform. Then we can write rho L of r dash, which is equal to rho L. So expression will become VA is equal to line integral of rho L into dl dash divided by 4 pi epsilon naught into r. So this is the expression of our potential at point A due to line charge distribution. Next we will see what is the expression for potential due to a surface charge distribution. Here also similarly we will consider a surface which has a charge density of rho s. surface which has a charge density of rho s, which is placed at a distance of r dash from the origin, and I am considering a small elemental area which has a surface area of ds dash. At point P, I am considering a small elemental area which has a surface charge density of ds dash. Surface area of ds dash. I am considering the surface charge density at this small elemental area as rho s of r dash. The surface charge density at this small elemental area ds dash is rho s of r dash. So this point P, now I want to find what is the potential at point A due to this small elemental surface charge. What is the potential due to this small surface charge on point A? The point A is the point which lies at a distance of capital R from this point P. Now what is the charge enclosed in this small surface area? You know the surface charge density, you know the surface area, so you can write dq, which is equal to rho s of r dash into ds dash. Rho s of r dash into ds dash, which is equal to dq. Now I want to find what is the potential at point A. So you know that the potential at point A due to this ds dash can be represented as small the potential dVA. I will represent that as dVA, which is equal to dq by 4 pi epsilon naught into r. So you know the expression for potential at a particular point due to a small elemental charge can be written as dq by 4 pi epsilon naught into r. So dq can be written as rho s of r dash into ds dash. Now this is the potential due to this small elemental area. To find what is the total potential at this, because of this total sheet on point A, can be found by integrating this with respect to surface area. So I can write VA is equal to surface integration of dVA. So what is dVA? dVA is rho s into r dash into ds dash divided by 4 pi epsilon naught into r. So substituting that, you will get VA is equal to surface integration of rho s into r dash into ds dash divided by 4 pi epsilon naught into r. Here also this rho s dash is a charge density at this small area. If the charge distribution is uniform, then I can write in the place of rho s dash, rho s into r dash, I can write rho s. So this expression will become VA is equal to surface integration of rho s into ds dash divided by 4 pi epsilon naught into r if the charge distribution is uniform. So next, this is the expression for potential for surface charge density. Next we will see the expression for potential due to volume charge density. So now here also I am considering a small volume of which has a volume charge density of rho v, and in that the volume I am considering a small elemental area dv dash, which is at point P. Now I have to find what is the potential at point A. This is a point A. I have to find what is the potential at this point due to this volume charge. What is the potential at point A due to this charge, which is at a distance of r from point P. The point A is at a distance of r from point P. Now how to write the what is the charge enclosed in this volume? So we can write dq is equal to what is the charge density? Rho v of r dash into dv dash. Rho v of r dash into dv dash. So because the charge density enclosed in this small area is considered as rho v of r dash, and the volume of this small elemental area is dv. So if you multiply both, you will get the charge enclosed in this volume. So dq can be written as rho v of r dash into dv dash. Now to find the potential at this point due to this small elemental area on point A can be written as using the potential expression at point A due to a small elemental charge or point charge. So you can write I will take the potential at point A due to this small elemental volume can be written as dVA. So dVA is equal to dq by 4 pi epsilon naught r. This is the distance between this point and this point. So dq by 4 pi epsilon naught into r. So what is dq? dq is rho v into r dash divided into dv dash. So substituting that in this expression, you will get dVA is equal to rho V into R dash into dV dash divided by 4 pi epsilon naught into R. Now, I want to find what is the total potential on point A due to whole volume. So, volume has a charge density of rho V. Now, we know the what is the, if you consider small volume in that volume, what is the potential produced by that small volume, you know. So, to find what is the total potential produced from that total charge enclosed by this volume, we have to integrate dVA. So, we have to integrate with respect to volume, we have to integrate, take volume integral of dVA. Now, to find potential, I will write VA is equal to volume integral of dVA. We can write the volume integral of dVA can be written as volume integral of rho V into R dash dV dash divided by 4 pi epsilon naught into R. So, the VA can be written as volume integral of rho V into R dash into dV dash divided by 4 pi epsilon naught into R. So, this is the expression for potential due to a volume charge in a point A. So, if the volume charge density is a uniform, then we can write rho V into dV dash divided by 4 pi epsilon naught into R. So, this is the expression for potential due to a volume charge. So, next we will see what is the expression for potential difference due to a infinite line charge. So, that we will see in the next video. So, in this video we saw what is the expression for line charge, what potential due to a line charge, potential due to a volume charge, and potential due to a surface charge. So, in next video we will see potential difference. What is the expression for potential difference, not potential. So, previously we saw what is the expression of potential at a particular point. Now we will see potential difference due to a infinite length line charge distribution. We will see that in next video. Thank you.